Alright guys, here's our first video lecture starting in section 11.2 with series. I know we had covered most of this, or at least a good portion of this series, this section in class. So I'm just going to kind of skim through the part of it that we've already covered, and then I'll pick up where we left off in class. Now, I'm going to go through these rather quickly. I mean, I don't have to spend a lot of time waiting for responses or asking questions because y'all can stop and rewind and replay or fast forward or whatever you want to do with these things. So I'm just going to go through the lecture, and if you have any questions or need further clarification with anything, you can email me. All right. But I mean, a lot of this, unfortunately, a lot more is going to be on you to have to let me know exactly what extra assistance you need. So whether it be from the lecture or from homework problems, you will need to email me. And working on testing, I'll send out an email to let y'all know a little bit more about how we're going to do testing, but I'll get to that later and send out an email to you when I've got that finalized. All right, so for now, we're just going to start with section 11.2 with series. All right, so we're talking about a series, which is essentially taking the terms of a sequence and adding those terms together. Right? So we had our definition of what a series was. We spent a lot of time talking about partial sums, taking the terms of our series and adding the first term, adding the first two terms, adding the first three terms, etc., and talking about the partial sums and looking at what happens to those partial sums. And so we came up with this, say our nth partial sum, which would be the sum of the first n terms. And so we're interested in what those partial sums were doing, because that would give us an idea of what the overall series was doing. If we're able to make an observation, if we saw that those partial sums were approaching some number, then the series itself would be approaching that number. All right, so the sum forms our sequence of partial sums, our series, our sequence S of n, right, which may or may not have a limit. And if that limit exists, it's a limit n approaches infinity of S of n equals S, exists as a finite number, then that's the sum of our infinite series. Right? So even though we're adding an infinite number of terms, we may be able to come up with a sum for that series. And I'll tell you, ultimately, going forward with this, it's not going to be so much about the sum itself, but whether or not it exists. Right? So can I determine whether a series actually has a sum or not? Being able to determine what that sum is going to be somewhat limited. Right? So we had our definition, right? Given a series A sub n, sum of those terms of the series, we let S of n denote the nth partial sum, which is the sum as I goes from 1 to n of A sub I. And so again, the notation I think can be tricky. Just be careful. Watch the indexes. Which sum are you talking about? That's our sum of the first n terms, right? As I goes from 1 to n. So that's our nth partial sum, as opposed to the sum of A sub n as n goes from 1 to infinity, which is the sum of all of the terms of our series. Now, if this sequence S sub n is convergent, and that limit exists, equals S, exists, then we said the series A sub n would also be convergent. So in order for the sum or the series to converge, the limit of its sequence of partial sums has to converge. Right? And then we said that number S then would be the sum of the series. Otherwise, we have a divergent series. And the sum of the series is the limit of that sequence of partial sums. Keep that in mind. That's going to come up over and over again in our discussion. Right? So if I'm looking at determining the sum or whether or not the sum exists. So here's another notation. It's just kind of just combining the two. Looking at this notation, the sum as n goes from 1 to infinity of A sub n, which is the sum of our series, is equal to that limit as n approaches infinity of the sum as I goes from 1 to n of A sub I, which this is our sequence of partial sums, right? Or the sum represents our nth partial sum. Right? And we're looking at the limit as n approaches infinity. I'd mentioned that arithmetic sequence. I tell you that wasn't one that's going to play a big part in anything, so I'm not going to spend any time with that. We did, however, get into this geometric series, and we talked a lot more about those. So our geometric series is a series that's formed, a geometric sequence, geometric series, where each term of the sequence or each term of the series is formed by taking the previous term and multiplying it by a constant. So we came up with this series of the form a plus ar squared, ar cubed, in each case where we're multiplying the previous term by this constant r. And so we came up with this notation. The sum as n goes from 1 to infinity of a r to the n minus 1. And then we went through these different cases with r. I said if r equals 1, the series would be divergent. And then we looked at if r is not equal to 1. Right, and we came up with this formula for the nth partial sum. And we said that s of n would be equal to a minus ar to the n over 1 minus r, as long as r is not equal to 1. And then we looked at the specific case where r was between 1 and negative 1. So, okay, well, let's look at what happens there, because that we had a little observation that we could base upon what we've seen before with r to the n. And if I take that number between negative 1 and 1 and raise it to the nth power, r to the n approaches 0 as n approaches infinity. Right? And so we looked at the limit as n approaches infinity of s of n, and we went through that little rewriting of it. And eventually we came up with that formula that the limit as n approaches infinity of s of n, that sequence of partial sums, is equal to a over 1 minus r for the geometric series with r between negative 1 and 1, or absolute value of r less than 1. And then we also made the note about other values of r. If it's less than or equal to negative 1, or if it's greater than 1, the sequence again would be divergent. And so we summarize that by saying that the geometric series, sum as n goes from 1 to infinity of ar to the n minus 1, is equal to a over 1 minus r. We can actually come up with a sum for this if the r value, if the constant that we're multiplying by is between negative 1 and 1. Otherwise, the series is divergent. So not only do we have a convergent series, but we can also calculate the sum. And this will really be one of the very few cases that we could actually do that. So like I said earlier, can you determine whether the series is convergent or divergent? That's one thing. If it's convergent, can you come up with the sum of that series? That's something else. And so the geometric series is one of the series that we can actually find the sum of if it is convergent. We know it's convergent if r is between negative 1 and 1. And then we can use that formula a over 1 minus r to calculate the sum, where a is the first term of the series, and then r is that constant that we're multiplying by. All right, so we did this example with that little series that I gave you, and we found the formula. We found r, right, to be negative 3/4. And since that r value was between negative 1 and 1, we knew we had a convergent series. And so we used our formula a over 1 minus r, where a was the first term of that geometric series, which was 3, plugged in our a, plugged in our r, and we came up with a sum for the series. And so, okay, that series is convergent, and I could tell you that the sum of the series is 12/7. Right? And that's where we had stopped. This next series that we're going to talk about, this harmonic series, this is a pretty important series. Going forward, looking at or determining whether series are convergent or divergent, which is going to be our primary task. Knowing things or certain things about certain types of series is going to be part of that. It's going to be helpful. A lot of times we're going to be comparing the series that we're working with to what we know about similar types of series, right? And knowing whether the series I'm comparing it to is convergent or divergent may be helpful in determining convergence or divergence of the series in question. So this harmonic series is one that's going to play a big role in that. So looking at this sum as n goes from 1 to infinity of 1 over n. So that's what we're calling the harmonic series. So nothing fancy there. The terms of that series, 1 plus a half plus a third, etc., etc. Looking at the partial sums, and s of 1, which is the first term, right? The second partial sum, which is the sum of the first two terms, 1 plus a half, s of 3, 1 plus a half plus a third. Actually, I'm interested in what happens from this point forward, from s of 4 on forward. Looking at s of 4, which is 1 plus a half plus a third plus a fourth. Look what we're doing here. I am replacing 1/3 with 1/4. So I'm making a comparison between the sum of these 4 terms and the sum of these 4 terms. And since 1/3 is greater than 1/4, then 1 plus a half plus a third plus a fourth is greater than 1 plus a half plus a fourth plus a fourth. As is with a lot of this, there's a reason we're doing this. There's a means to the end here. So watch the pattern that's going to develop over these partial sums that we're going to look at. 1 plus a half plus a 4 plus a fourth is then 1 plus a half, or 1 plus 2 halves. I'm then looking at the eighth partial sum. 1 plus a half plus a third all the way up through an eighth. And again, I'm comparing that to this sum, which again is the sum of 8 terms where I'm replacing 1/3 with 1/8, 1/5, excuse me, with 1/8, 1/6 with 1/8, 1/7 with 1/8. Back here, again, I replaced 1/3 with 1/4. But since each of these is smaller than the one that they're replacing, then our S sub 8, that eighth partial sum, is going to be larger than that sum, which is then 1 plus 2 halves, right, which was this guy, plus another half. Right? 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4/8 or a half. Or I get 1 plus 3 halves, okay, for the S sub 8. So again, just again, follow this pattern. Now I'm interested in the final result, so if you that seems a little bit confusing, just kind of digest that. But S of 16, which is the next partial sum we're looking at, the first 16 terms, and we add all those guys together. And I went through a similar process of replacing the fractions with something that's smaller than those fractions in the original series. And we come up with this sum of 1 plus 4 halves. But our original series, our original 16th partial sum, is larger than the sum of the terms that we have, which is 1 plus 4 halves. So there's a pattern that's developing here. Notice for S sub 4, it's greater than 1 plus 2 halves. For S sub 8, S sub 4 is greater than 1 plus 2 halves. S sub 8 is greater than 1 plus 3 halves. S of 16 is greater than 1 plus 4 halves. S sub 32 is greater than 1 plus 5 halves, and so forth. S of 64. But notice each of those subscripts, 4, 8, 16, 32, 64, that's 2 to a power, right? That's 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th. And notice that the numerator in each of those fractions, 2, 3, 4, 5, and 6, corresponds to that end value. And so we end up coming up with this formula. So when all is said and done, and as usual, I'm interested in the final result here. In general, we could show that S sub 2 to the nth power is greater than 1 plus n over 2. And again, each of those is coming from the partial sums of our harmonic series, sum of 1 over n. And I'm looking at the partial sums, S sub whatever, right? And we just came up with looking at the specific ones where the subscript is 2 to the nth power. And we showed that that's greater than 1 plus n over 2. Now, what does that do for me in terms of our series? Well, if you look at the limit as n approaches infinity of 1 plus n over 2, right? That's going to approach infinity. Because as n approaches infinity, n over 2 approaches infinity, and 1 plus that, of course, would approach infinity. But here's our kind of that idea of the comparison that we've talked about before. If I can compare my series to something that we know something about, right? So this 1 plus n over 2 I know approaches infinity as n approaches infinity. So that means S sub 2 to the nth power has to approach infinity because it's greater than that sequence. Right? And so by using this observation, we can show that S sub 2 to the n is a divergent sequence, which is a representation of our sequence of partial sums. Right? Because those are just some of the partial sums, and I'm taking showing that those partial sums as n approaches infinity approach infinity. So in general, our sequence of partial sums, S sub n, would have to approach infinity, giving me a divergent sequence. And since the sequence of partial sums is divergent, as we had mentioned earlier, then our harmonic series would have to be divergent. okay, because its sequence of partial sums is divergent. So here's the big observation, and ultimately this is the takeaway from this. So our harmonic series, sum as n goes from 1 to infinity of 1 over n, is a divergent series. Theorem. Now this next little piece is going to be very important in terms of in general observations, so pay particular attention to this part of it. This theorem that if the series a sub n is convergent, then the limit as n approaches infinity of a sub n, which what is a sub n? That's the terms of the series. That limit has to be 0. What does that mean? Well, that means if I look at the terms of the series a sub n, then as n approaches infinity, those terms would have to be getting smaller and smaller and smaller. Those terms would have to be approaching 0 in order for the series to be convergent. And that should make sense, because if I'm adding an infinite number of numbers or an infinite number of terms, if that series is to converge, if I'm going to actually be able to come up with a sum or determine that that series has a sum, the only way that happens is that at some point, even though you're still adding stuff to the series, what you're adding becomes so small, becomes so insignificant that it doesn't affect the sum of the series. So it makes sense that the terms of the series itself have to be approaching 0. The limit as n approaches infinity of a sub n has to be 0 if the series is to be convergent. Now, the converse of that is not necessarily true. And we've said before, we got to be careful with what these things say. Don't read more into it than what's there. The converse would say that if the limit as n approaches infinity of a sub n is 0, then we have a convergent series. And that's not necessarily true. The harmonic series that we just looked at, right? The sum as n goes from 1 to infinity of 1 over n, where that limit as n approaches infinity of 1 over n is 0, but we showed that that was a divergent series, not convergent. So be careful with this. So if the series is convergent, we know that the limit of the terms of the series has to approach 0. But just because that series approaches 0, that sequence approaches 0, doesn't mean that the series is convergent. And so that's where we'll have to get into all these other different tests and processes that we're going to have to use to try to make these determinations about convergence and divergence. So again, remember that with any series, sum of a sub n, there are two sequences in play. First, you have the sequence a sub n of the terms of the series. Right? So if we're just listing out the terms of the series itself. So that's what we're talking about above, where the limit of that sequence, right, this guy has to approach 0 in order for the series to converge. And then we also have the sequence of partial sums, right, which is the other one that we've been talking about. We say, okay, we'd have to look at the limit of s of n. And if our series is to converge, then the limit of s of n, the sequence of partial sums, would have to converge. Right? So if the sum of a sub n converges, and here's our really, really major importance, I'm going to put an extra block on this one. If the sum of a sub n is a convergent series, then two things have to be true. The limit as n approaches infinity of the sequence of partial sums s of n has to equal s, and that would be the sum of the series. And the limit as n approaches infinity of the sequence a sub n, right, the sequence of the terms of the series, has to approach 0. Right? So that's our individual terms. The values have to get smaller and smaller and smaller. And this is typically the one that we look at first, right, leading us to this test for divergence. Now, this is going to be our first kind of major test that we're going to use to determine convergence or divergence of series. Don't forget about it. It's the simplest test we have available. We're going to end up talking about a bunch of other tests that are a lot more complex, a lot more involved, a lot more complicated. Don't forget about the basics. This is always the first thing that we check. Since we know that the limit as n approaches infinity of a sub n has to be 0 in order for our sequence to converge, then let's check that first. Let's test that first. So if the limit as n approaches infinity of a sub n is not equal to 0, or if it doesn't exist, then we know the series has to diverge. Now, of course, what's going to end up happening is a lot of the series that we're going to look at the sequence of the terms, limit as n approaches infinity of a sub n, is going to approach 0. And what does that tell me? It tells me nothing. All I know is if it's not 0, or if it doesn't exist, then I can tell you that that series is divergent. But if it is 0, it doesn't tell me anything. And that's what's going to lead to our other tests that we're going to have to talk about. It's okay, so then how do I make that determination? All right, so here's an example. Show that the series sum of n as n goes from 1 to infinity of 1 over 5n squared squared over 5n squared plus 4. Show that that series diverges. So the first thing we always look at, and again, this is always my first test for any series. We look at the limit as n approaches infinity of a sub n, right? The sequence of the terms, which would be the limit as n approaches infinity of n squared over 5n squared plus 4. And then we're evaluating that limit normally. Now, this just goes back to basic limit evaluation. You could use L'Hopital's rule here if you wish. It's an infinity over infinity situation, or the one that I have written out with, that we've used before with rational functions. So either way, we're evaluating that limit, and I can show you that the value of that limit is 1/5. And since 1/5 is not equal to 0, and that's the limit as in approaching infinity of our sequence of the terms, then I know that that sequence is divergent, because if it's going to converge, that has to be equal 0. Okay? The fact that it's not 0 tells me it's divergent. Now, if it was equal to 0, what would that tell me? It would tell me nothing. I would have to find another test to make that determination. Okay? And that's the part that gets everybody in trouble. So, if that limit is 0, it doesn't tell me a thing. Here's another theorem. Now, this one's pretty straightforward. Nothing fancy here. If we have two series, sum of a sub n, sum of b sub n, that are both convergent series, then the following series are also convergent. The sum of a constant times a series, the sum of the sum of series, the sum of the difference of series. Those would all be convergent. And we can calculate the sum of the series by looking at the sum of the constant times the series is equal to the constant times the sum. The sum of a sum is equal to the sum of the sums. Let's say that 3 times fast. And then the sum of a difference is equal to the difference of the sums. And so nothing real fancy there. That's pretty straightforward, I think. This last example in this section, writing a fraction, writing a decimal as a fraction. And if I said take the fraction 6.2, for example, and put that or write that as a fraction, how do you do that? Right, we take the number, we drop the decimal, we place it over the last place value. So since 2 is in the 10th place, I've got 62 over 10. And we could simplify that, right, to 31 over 5. But that's the basic idea, right? We take the decimal, place it over the last place value of the number, drop the decimal, and there's our fraction equivalent. And that works fine as long as the fraction that we have, that the decimal that we have is a terminating decimal. And we know what the last place value of the decimal is. In this one, we're looking at a repeating decimal, 6.254. And I'm looking at writing that or expressing that as a fraction. Well, I can't do what I just did with the 6.2 because the 54 is repeating, right? I mean, if I write that decimal out, I need a little more room. So it's 6.254, right? 54, 54, etc., etc., etc. And if I say, okay, well, let's just stop it at any point, the fact that these keep repeating, if I say, okay, let's stop it here and use that as my last place value, well, that doesn't work because I have more 54s coming after that. Right? So the question is, well, how do you take a repeating decimal and represent that as a fraction? Well, look at the repeating part of it. So I've got the 6.2, and then I have the 54s that are repeating, 54, 54. If I represent that decimal as a sum, 6.2 plus the repeating part, that's 54, last place value is 1,000, right? Which is 10 cubed, so 54 over 10 cubed. If I put another 54 on that, then that would be 54, where the last place value would be hundredth thousandths. or 10 to the fifth. And then again, another repeating 5, 4 would add another 2 place values, raising that to 10 to the seventh. So in other words, each time you tack on those repeating decimals, the 5, 4, you're tacking on 2 decimal places, right, which is 1 over 10 squared. So notice in each case, the previous term, or the next term, is the previous term times 1 over 10 squared. And that's exactly a geometric series. And you can do this with any repeating decimal. It's simply whatever the repeating part of the decimal is, and expressing it as a fraction, adding in, as a sum, adding in each of the repeating portions, decimal digits or digits, however many you have, and whatever the number of digits is that's repeating, that's going to be the exponent on the 10. So if I had one repeating digit, then I'd be adding 1/10 each time. If I have 2 repeating, as I have here, I'm adding 1 over 10 squared. If I had 3 repeating, then I'm adding 1 over 3 cubed. Now I say adding, plus the digits themselves, right? So our R value is 1 over 10 to the power, where the exponent is simply the number of repeating digits that you have. And so recognizing then that this is a geometric series with R equal to 1 over 10 squared. Now be careful of the A value here. This is where you have to watch. All right, so where exactly is the series beginning? The geometric part of this series begins here. You have that first term 6.2. That's not part of the geometric series. That's not part of the repeating portion of that number. So you're only including the repeating portion to set up your geometric series. And then I'm just repeating the numerator, right, because I'm repeating the digits, and the denominator of that fraction changes, where I'm multiplying by 10 to whatever power, depending upon the number of digits that are repeating. So that gives us the first term of this geometric series as 54 over 10 cubed. With our R value of 1 over 10 squared, I can then rewrite that repeating decimal as the non-repeating part, 6.2, plus there's our A over 1 minus R, which is the sum of the geometric series. All right? So, recognizing first the geometric series. Secondly, what's the R value? What's the A value? What's the term, or the first term of the geometric part of the repeating part? After that, we're just plugging it into the formula. Right? So A is 54 over 10 cubed. R is 1 over 10 squared. Plug that in. Simplify. And we end up with 344 over 55. Now, you can try this on your calculator, too. Take the decimal 6.254. Right? Put that into your calculator. Convert it to a fraction. Hit your math button and then enter. And then it'll convert it to a fraction, which is not this. Tack on another 5, 4 and do it again. Tack on another 5, 4 and do it again. After you tack on enough, right, you'll have to put enough 5, 4s repeating, and then when you convert it to a fraction, eventually at some point you will get this, but you have to have enough of the 5, 4s tacked onto it. This is always a good test question. I'll give you one of these come test time, where I'll give you a repeating decimal. I'll ask you to convert it to a fraction. Okay? All right, well, that's that section. That is section 11.2. So I'll see you in the next section.